recording here. The commonly used authentication mechanism. So the methods to steal or pilfer user password would be guessing, okay, social engineering, dictionary attacks, and password sniffing. So we're going to look at each of these possible techniques. Okay, guessing is the easiest way to steal a password, to find out a user's password once. So for instance, the following is a survey of commonly used passwords. Okay, this was done a few years back. A lot of users simply use some phrases or strings they can remember. Hence, when an attacker gets a file of usernames, and they can first try to see whether these commonly used passwords would match any of those usernames. Now, again, when we talk about security, network security, we don't usually mean the target would be a specific entity. Okay, so any machine will be the target. So let's say if you have 1 million usernames and about 10%, I'm sorry, 10% too big. Maybe you have 1 million usernames and you have maybe 0.1% of users that use these common passwords. Okay, then of course you can get into a lot of users' accounts. Okay, so this is a guessing attack.
Professor?
The next attack
Yes.
is
how would guessing fit in with sites that have like a certain amount of attempts before they lock you out?
Oh, you write a program, you go into each username, and then you use some of these passwords. They usually give you a few options, right? So you don't, so as I just said, that defining success rate is not saying that if I want to attack that account, I will be definitely successful. But you are looking at, let's say, 1 million accounts, and you just try them more. And if some of them you get in, then you get in. Would that make sense?
Yeah. So it's kind of
Right?
just a bit slower.
Oh, yeah, exactly. Because
okay.
when we talk about network security attacks, we just think of every computer on the internet is a target. So once you get into a machine, then you can use that machine and launch some other thing, do some other things, launch other attacks.
Okay, thank you.
Yeah. Social engineering attack, methods of using social skills to steal secret information. Okay, so these two are common techniques. One is physical impersonation. The attacker pretends to be a different person to delude the victim. Okay, so for instance, they may pretend they are some of the managers at the corporate headquarters, and they call a secretary in a remote office and saying that they needed to get into the system to see some data because there is a meeting going on, they need to cut a deal, but he's the computer he got into was down, so he couldn't see the data he used to be able to see. Now he wanted to see that data in a remote office, that kind of thing. So that is physical impersonation, social engineering. The other one is in an electronic form, which is called phishing. Okay, so this is the most common form of mass social engineering attacks. Okay, so basically what these attacks is to send you a disguised email message and and ask for your usernames and passwords, or send you a masquerade websites that look like a real website you usually go to, and then pop up a login window asking you for your username and passwords, and then of course the attackers can catch that information. Okay, so the textbook has a real phishing information example. I'm sure if you use internet a lot, you should have seen such phishing examples yourself. Okay, so this is a real phishing attack example. Okay, so in general, any phishing email would contain a link to a bogus website called a phishing site. Okay, so there are other forms of social engineering attacks. For instance, this is a common method you saw detectives would usually use, like you saw it from a TV series called Columbus, right? They collect recycled papers from recycling bins and try to find out information that may lead to your username and passwords. Or electronically, they can use a web browser pop-up, okay, pop up a login window and asking for user login directly. The defense mechanism is to use anti-phishing extensions of web browsers to prevent such pop-up windows from popping up on your screen. And of course, from the user's point of view, you should be very vigilant when you saw such windows pop up, and don't do it. Okay, so don't just type in your username and passwords when you see that window. Okay, the next password filtering attack is dictionary attacks. So the user passwords are stored in so on any system, they don't store user passwords in plain text. Instead, they store an encrypted version of users' passwords. Okay, so so let me draw up something to show this. All right. So so usually you have a username and then password. So that password to the user is in plain text, but that plain text password is not stored on any computer system. Instead, so let's say this is W. Instead, it applies a hash function Okay, so W is a plain text, and the encrypted version of this password is is H of W. H here is a hash function or cryptographic hash. So your username, let's say this is you, then this, maybe it's a WU, so indicate this password is for you. So this information gets stored in your computer. So when the user U logs on, he enter his password, he enter his username and then enter his password, and then the system computes H W sub U. So if this one, okay, so if this matches with this one, then of course the user U is authenticated. So that is the common mechanisms for storing passwords. Okay, in Unix and and Linux operating systems, passwords are stored in a file name, in a file named shadows under this particular directory. So this is system directory /etc. In Windows XP and some other similar operating systems, passwords are stored in a file named SAM, which is stored in the systems registry. Okay, let me erase.
Professor?
Yes.
So you're saying that this is how passwords are stored in computers. Is this for passwords that are for computer programs that are on the computer, or is this also for websites? Because I know that
this is for the user accounts.
User accounts, because I know that a lot of the passwords that we use these days are for things that are online, and I wasn't sure if those are stored differently.
Right now, we are looking at operating systems. So you have accounts on that machine, and that's how it's stored. Yeah.
All right.
Erase this, and then now we move to the next slide. Okay. So a typical dictionary attack proceeds as follows. First, the attacker needs to obtain information of usernames and the corresponding encrypted passwords. And then run the encryption routine H, okay, used by the underlying system on all possible passwords. Okay, so these possible possible passwords. So these passwords could be English words, names, dates, and some combination of these, and maybe also some numerical values. Okay, so these are possible passwords. Okay, so now let me draw up this again. Okay, so let's say the attacker gets a particular user and gets his encrypted passwords. So now he wants to find what this W sub U is. So what he can do, of course, he will try or possible W use. Okay, so let me put a prime here. Okay, try all possible passwords and then compute, because this H is public knowledge. So this routine is public because it is the standard things under the corresponding operating system. Try all of them. Okay, and see whether this is equal to HW. Now, we know that this H is a hash function. So even though this particular WU prime may not be identical WU, but they have the same hash. So that would count too, because what you need to enter on the system is this, because this gets stored in the system. So you get WU prime and they have the same hash, then you will be allowed to get in. Okay, so that's a common method of dictionary attack. The reason it is called dictionary attack is you try all possible passwords, and one common way to get them is to get a dictionary, and that's also passwords people tend to use in early days. Okay, so but then from efficiency point of view, it has a problem. Okay, so the procedure I just described, you could either do it on the spot. So once you get a user name and password, and you try all possible passwords, so you do it on the spot. But then you know this takes tremendous time because there are so many possible candidates. So that takes time. Okay, it's not efficient. Okay, the second is you pre-compute a you pre-compute a user you pre-compute a table where you have for all possible passwords, you pre-compute its encrypted value and store on the attacker's system, right? But then that's too big, right? So that table will be huge if you have to consider all possible passwords. And there is a technique to make this process more reasonable, which is a technique called rainbow table. Okay, so it helps reduce the table size and make the computation manageable. All right, so the idea of rainbow table is the following. Now let me start a screen so I can draw up something. Okay. So as we said that, so what we want to do is to make dictionary attack manageable. You cannot do it on the spot by trying all possible passwords, and you cannot also pre-compute a table with all possible passwords because that will be too big. So the compromise would be I store part of the information. So here's the idea. So now let's say I have a user password W, which belongs to a set P that is a set of all possible passwords. For instance, if you use a dictionary, so P will be your dictionary. And of course, you can add some dates, you can add some names, and then of course you can enlarge that P. Then you can put some numbers, other symbols, right? So, but then of course this P could be huge. But nevertheless, what the idea is this. So I randomly select a W in P. Of course, let's say this is a legitimate user password, and what gets stored is on the system is h of w. Okay, the goal is to find w and to find w in a more efficient way by taking a trade-off of space and time, right? So you do it on the spot, takes too much time. You do it, you pre-compute every possible w, you have to store lots of data. So I want to find a middle ground. So then the idea is, first of all, we know w. So this is u. So h of w is longer than w. Okay, so maybe this w is 8 characters long, 10, 18, and so on, right? So usually it won't be too big, too long. But h of w tends to be longer because this h is a hash function. So then when I see this, in order to find a candidate w prime, I need to reduce this length. So to reduce this length, I am going to use something called a reduction function, R. So this is called reduction. Okay, so this reduction will hopefully, so this is a reduction function, will hopefully, when I apply R on this h of w, it gives me a password in P, okay? So that is the idea. So now what I would do is, as I said, I randomly select. So this is randomly selected. So this is a selected at random. And then what I'm going to do is I'm going to start from W, and then I'm going to apply H. Okay, so let me say apply H. And what I'm getting is H of W. And then I'm going to apply R. I'm going to get, let's say I get W1. So that I hope is in P, okay? And then I do this a few times. Apply H again. I get H of W1 going R. I get W2, right? I do this a few times. So this is H of W2. I do this a few times. Finally, I'll get, let's say, I get Wn. And then apply H. I get H of Wn. Let me use K here because N usually tends to be, people would think K is fairly big, but N would be fairly big a number. But well, of course, N, as long as you know N is some number, that would be fine. So let me just keep N here. All right, so then the idea then, now let's say what I need to store. So this is a train, right? So this is a train. So what I store is the beginning, W, and the end. Okay. Now, so why is this useful? So now, assuming I get H of, let's say I get H of W prime. Okay, so this is the password I got. Okay, assuming, okay, this W prime appears in one of these. Okay, so if W prime is in the string, in this chain, then I can find it by looking at this. Okay, so I start from W. I do this. I encrypt H, reduce it until I find until somewhere. Let's say this W2 is W prime. Then I can find it, and then I know this H of W2 is H of W prime. So this is the plain text I found, W2, right? So then I found this password. But however, of course, you know, this is the best situation. So it may not happen in the string. So that means I need to do more strings. Now, this string should not be too long, right? So this string, you don't want it to be too long. So this N should be manageable. Should not be too
Professor?
big. Should, yes.
So just so I'm properly understanding this, so W prime is the guess that we have for what the password is, right?
The W, well, we got H of W prime.
Yes.
We
How do
don't know
we
what,
get the hash function?
Oh, by going to somebody's account.
Okay.
The system's account. For instance, in early days, if you look at Unix systems, you can see these password files that you can download with all the other users, their usernames there, and also
Okay, so
yeah.
So the hash function is publicly available somewhere.
Oh yeah, you must have that first. Otherwise,
right.
yeah, then you cannot do any dictionary attacks. Yeah.
All
so,
right.
So assuming you obtain, let's say you obtain a pair of a username and it's a password. So that's what you got from going to somebody's system.
Yes.
Okay.
Yes. So you got the hash of the password.
That's right.
And so from that hash, you can figure out what the hash function is. Is that what you're saying?
No, from that hash, we are trying to figure out what that
What the password
is. So we're going to find another W because that W prime is the one you can enter.
Yes.
On the system login file, not the hash code. So I want to find HW prime so that this is equal to this. So if I can find it, then I can pretend I am user U by putting user login name U, and then W prime as its password, then I can get in.
Okay.
Would that make sense?
Yeah.
Yeah. So then, of course, this is a dictionary attack. We could either do it on the spot, but then you have to try all possible W prime. So that's a lot of computation on the spot. So then the other way is I pre-compute all possible W prime, but then again, that could be big, right? So this table would be huge. It may be even, it's so big you cannot even put the whole thing into your memory. So rainbow table is just a compromise. So I still store something, but I don't store the entire table.
Okay.
Well, that makes sense.
Yeah.
Yeah. And then because I store something, so I cut down my computation time as well.
All right.
Yeah. Not be too big. Okay. So what happens if your W prime does not appear in the string? Okay, so that means you need to do more of these trainings. So that is the idea of a rainbow table. Okay, so let's, so now I'm going to do a few of these. So I get W1, randomly selected. And then I do W2. And then I do a bunch of these, let's say WM. Okay. And then I create a table, a train. So let me call it 1, because use this to get the intermediate ones, right? So you get H, you get R, you get a few times, eventually you get to, let's say 1N. And then what I get to store is H of W1N. So each of these is a train. So this is H of WM. Let's say their lengths may not be exactly the same. Let's put N1 here, N2 here. Just indicate their lengths. Doesn't have to be exactly the same, but it's easier to have the same size for each chain. So then what I get to store is this. Okay, I get W11, and the next value will be H of W1 and sub 1, W21, H of W2 and sub 2. So the last one, WM1, H of WM and sub M. So this is a rainbow table. So what I want, the ideal rainbow table, is that the ideal rainbow table is that none of these strings overlaps. No strings overlap. Okay, that's one. And I also hope this covers my possible password space. Okay, so that means all the intermediate. So all passwords, all possible passwords are covered in these strings. Oops. In these strings. So let me rewrite this. Okay, so that way I will be sure I can always find a password in this table. Of course, in reality, it is just hard to achieve, but nevertheless, you can, when you have a rainbow table, and I have captured H of W. So the idea then, to find out whether this W appears in one of these strings by doing some computation, but not the entire thing. Okay, so now let me start a page. So, so we first want to see, let's say we got H of W. So this is captured. I capture this. Okay, so this is captured. And then what I want to is to try to see with, look at the table, the rainbow table, to see if there exists I such that H of W is equal to H of the ith row. Okay, so if it is, then I can hopefully, okay, I will start from WI1, and then, so this is H going to WI2 and so on. So this is I and I, H of I and I. And then I can, so this is the one I find. Okay, that gives me the same hash function. Okay, so this W, as I said, may not have to be the same as this one, as long as the hash is the same. So if there is no such I, so if no such I exists, so what you want to do is now we get, so this is HW is what we get. I'm going to reduce its length and then apply H. And then repeat the process to see whether there is one last one, there is one row, one train, okay, that even though such I exists, and then we find and try to find if there is J such that after this it's equal to H of Wj and J. Now this J could also be I as well, okay? If this is true, then you can start, okay, from that J, and then you can find your passwords. Okay, so how long you have to do this? The ideal situation is that you only need to do the maximum of Ni times. There you can stop, because after that, if none of these matches, then you will know your password will not appear in these strings. Okay, so that is the idea of using rainbow table to launch a dictionary attack. Now let's go back to our slides. So I already explained how rainbow table works. Okay, so these are just formal writing of what I explained earlier on a whiteboard. Okay, so the last attack will be password sniffing. So this has to do with the network communication. If you do a remote logins and you put in your username and passwords, if that password is not encrypted when it's sent out, and then the attacker just needs a let's say sniffer, network sniffer, right, a Wireshark. by putting in its own router on the path you would go through, then he will be able to learn your password. Okay, if the password is encrypted, then of course he needs a dictionary attack. All right, so what would be the defense method? Of course, encrypt all messages, including login information, using SSH and HTTPS, because your passwords will be encrypted. But as I said, even the passwords are encrypted, they are still can be learned by dictionary attacks or guessing, right? So that means we need to make sure our passwords are complicated enough to defy any dictionary attack. Okay, so there are several rules you may want to follow. So rules to help protect passwords from pilfering. Number one, use long passwords with a combination of letters, capital letters, digits, and other characters that you can find on your keyboard. Dollar sign, pound sign, at, or semicolon, that kind of thing. Okay, do not use dictionary words directly. Do not use common names and dates. And do not reveal Okay, so let's continue.
Did he just disconnect?
I think we just lost the professor.
Yeah, it just made me the host for some reason.
You got chosen to be the new king.
Yeah, go ahead and just take over for us, would you?
Yes, please continue telling us about passwords.
The best password is password.
There you go.
Just throw in the @ sign in there and it's uncrackable.
Okay, I'm sorry. I got a Wi-Fi issue somehow that my connection was cut off. Now it came back. Very unfortunate. So we resume. Define social engineering attacks. If you have to give out your password, do not do it over the email. Do not do it over the internet. Instead, do it face to face. Number 3, change passwords periodically and do not reuse old passwords. Number 4, do not use the same password for different accounts. Okay, so number 3 is also a measure to make your possible passwords candidates. The set of possible passwords, capital P, as big as possible. Number 4 is to protect yourself in case one of your accounts was compromised. You still have protections for the other accounts. Number 5, do not use remote login software that does not encrypt user passwords and other important personal information. So this is this defines network spoofing.
Professor?
Yes, sorry,
It's
network
very
sniffing.
blurry. I think the quality is low on the video.
On the video,
Or no, it's not, but there we go. All of a sudden it cleared up.
well, it looks fine here. I don't
Okay.
know. But of course, I have this is pre-recorded, so you can always look at the one posted on Blackboard. Shred all discarded papers using a good paper shredder. Okay, so that social engineering won't work on your discarded papers. Number 7, avoid entering any information in any pop-up window and avoid clicking on links in suspicious emails. In addition to passwords, there are other user authentication methods that we mentioned earlier. You could, for instance, you could use biometrics of unique biological features. That means connect biometric devices to a computer, usually just some kind of sensors, such as fingerprint readers or fingerprint scans, retina scans, facial recognition software, right? So these can also be used. So we have these methods on smartphones, or use electronic passes. Once you authenticate yourself, then you will be issued an electronic pass. Then you can use that pass to authenticate yourself for other services without retyping your passwords. We will talk about this when we talk about Kerberos authentication protocol in chapter 5. And also when you use web browsers, you have a cookie when you visit a web browser. So that cookie also has your personal information, so that when you visit one page that you need to authenticate, when you So you first visit a page, you authenticate yourself, and then for subsequent pages, from that authenticated page, then you don't need to retype your password. So because your information is stored in your cookie, and that cookie will go with your request, URL request. But the password authentication methods is still by far the easiest method. The other network security attack is identity spoofing. Identity spoofing attacks allow attackers to impersonate a victim without using the victim's passwords. Okay, so some of these attacks include man-in-the-middle attacks, message replays, network spoofing attacks, and software exploitation attacks, or so these attacks are also referred to buffer overrun or buffer overflow attacks. In a man-in-the-middle attack, the attacker will first compromise a network device or install one of its own between two or more users. Then he would use this device to intercept, modify, or fabricate data transmitting between these two users. So in this figure, A and B are legitimate users. They are communicating with each other, and then the attacker sits in the middle by putting in his own device. Okay, so and lure user A to use the router he controls. Hence, the attacker captures that packet from A to B. Likewise, he can also capture that packet from B to A. Okay, so he can then he can modify these packets. Okay, so the defense measure for man-in-the-middle attack, for this type of man-in-the-middle attack, is authenticating users. So A needs to authenticate herself. So Alice needs to authenticate herself to Bob, B, and likewise, Bob needs to also authenticate himself to Alice. And to avoid modification, so that authentication can also be used to avoid being seen, so to avoid the content of the packets being seen from the attacker, encryption can be used. Next is message replays attack. Okay, so when you replay or resend a message, you want to make sure that message is a replay. Okay, so to launch such attacks, the attacker first intercepts a legitimate message and transmits that message at a later time to the original receiver. For instance, an attacker may intercept an authentication pass of a legitimate user and then uses to impersonate this user to get the service from the system later, at a later time. The defense mechanism is to attach a random number to the message, okay, a unique random number to the message. So this number is referred to as nonce. So that, so for instance, when Alice sends a message with a nonce to Bob, then Bob will record that nouns in its system. Later, when the same message comes in, Bob will check that nouns in that message. If that nouns already appears in his storage, in his record, okay, then Bob will know that message is a replay. But the problem of this approach is that Bob needs to store a huge number of messages, okay? So this solution is impractical, okay? So there are so many packets going back and forth, and you can't simply just store all the announcers. So to overcome this problem, a easy way is to not use a random number. Instead, you use a timestamp on that message, okay? For instance, that message was sent at 10 o'clock. Then if Bob receives it either before 10 or quite a bit later than 10, then Bob would know this message is a replay. Unfortunately, this method has a drawback because in a computer system, the current technology cannot guarantee 100% synchronization. So in other words, each built-in clocks of each machine are off, okay, slightly off. So they are off by a little bit. So in other words, the best technology, the synchronization technology, can guarantee that each host computer on a network can be synchronized within a small window, Okay, so this delta t, within this delta t. So let me highlight this. Okay, so with this delta t, right? So you want to set, say, you put a timestamp at time t, but time t on your local machine would be time plus delta t on a different machine. Okay, so this delta could be plus, could be positive, and could be negative. Okay, so that means that so you have a t, then within a small range. So this is negative delta t. This is positive t. So let's say this delta t could be positive and negative. Then all the machines on your network, their local clock will be in this range. Okay, it will be in this range. So that gives an idea. We should use timestamp and nouns together. Within this timestamp, within this interval of the timestamp, we will need to store all nouns that happen within this time range. Okay. Now let me remove this and go to the next slide. I have this one here. Okay. So network spoofing So once again, let me open up a whiteboard. So so for each message, let's say this is my message, what I want is a timestamp. So this is the first, I want a timestamp. But then I also want to announce. Okay, so then let's say for each I add a timestamp and announce for this M, and then I send it over. So this is Alex. Send it over to Bob. So Bob sees this message with timestamp T and N. So now for each time, he will, in this range, so this is T minus delta T and T plus delta T. So this is the maximum error range, which is a very small. The current technology can guarantee this delta T is a very small number. So within this range, Bob will keep all the nonces it receives. So in other words, for any message, look at it's a timestamp. So that timestamp falls into this category, then it will store all the nonces that he saw. So when time goes by, some of them, so for instance, if it's a T1 is in this range, okay, so in a smaller range, so when the range goes bigger, when the time moves on, then some of these can be removed. So can be removed from this table. So they are old with a old time can be removed. So so this way, Bob doesn't have to store a huge number of nonces. Only in a small time window, he stores all the nonces. So this way, message replays will be detected. Okay, so this is the common technique. So you would need a timestamp. You would need announce for each message to detect message replay attacks. Okay, so that. Now let's do an exercise to figure out how big a time frame we need to keep nonces. Okay, so we know that let's say a packet comes in. So a message comes in with a nonce, with a timestamp T and with a nonce N. So so when I see the message with this T and N, since we know that this T is from the sender's T, so my local T, so the sender's T, so the local clock would be in the range of delta, t minus delta t, t plus delta t. Okay, so let me make it clear. So let me put this t1 here. Okay, so that will be t1, t1. Now this delta t is constant. Okay, so this is the maximal error. So it's a constant. So for any t, for any time t, so this delta t is the same. So when I send this t1 on my local side, in this range, I need to keep n. So let's also put it n1 here. Okay, so now when is this n1 to be removed? In other words, how long I would need to keep this n1? So of course, when the time, let's call it t2. Now let's call it another one. So let's say I got t2 here. T2 is greater than T1. Okay, so now in this range, I will need to keep this. So that means if my T2 is here, let's say this is the time axis. So then this N1 can be removed from this interval. So which means when T2 minus delta T greater than or equal to T1 plus delta T, that means when T2 is greater than or equal to T1 plus 2 delta T, then, so this is when, then N1 can be removed. So you don't have to keep this N1 no more when this time T2 is greater than T1 plus 2 delta T. Okay. All right, my time is up. So we didn't finish this chapter yet. So I will adjust some of the deadline. I will adjust the deadline for quizzes and discussion board to Wednesday, so that next Monday by next Monday we should be able to finish up this chapter. Okay. All right. Are there any questions?
When are we going to hear about details about the project?
After the job day, then I will go over the project, because right now some people may still come in, some people may decide to job. So maybe the week after next, or next Wednesday, then I should be able to talk about it. I'll check when that deadline is.
Okay, thank you.
Yeah. Okay then. So I'll see you next week. Bye-bye now.
Thank you.